Thanks, Victoria.
So what is a drip irrigation system? It consists of a pump connected to a piping network where there is a pipe laid out along every row of crops in the field. This is in contrast to more traditional systems, or to more traditional methods, specifically flood irrigation, which is what is used commonly around the world, where you flood the entire field with water and you wait for the water to seep into the ground. In drip, the pump draws water from a source, pushes it through one or more filters and a fertigation unit, which allows you to inject fertilizer into the water, and it releases the water at every single plant directly to its root zone through one or more drip emitters. And this targeted, slow application of water helps avoid evaporative losses and losses to deep percolation that are associated with sprinkler and flood irrigation. So overall, in previous studies of drip compared to other irrigation methods, drip has been shown to increase crop yields, but also decrease water consumption compared to flood irrigation by up to 70%. Despite these benefits, only 7% of irrigated land is currently using drip irrigation. And one of the main barriers to adoption is capital cost, specifically the cost of the pump and the piping network. This is especially an issue for smallholder farmers, and this population of 2 billion people of smallholder farmers is our target market. They are highly sensitive to initial cost. Also, a lot of these farmers live in areas where the electric grid is unavailable or highly unreliable, and so they need an additional power source in order to run the pump, which is usually a diesel generator or a solar array, which increases system cost even more. So one of the main drivers of system cost is pressure loss throughout the piping network and the emitters. Therefore, we've been pursuing a bilateral approach to reduce cost of solar-powered drip systems by two means. First, redesigning drip emitters to operate at lower water pressures, and two, looking at the system as a whole and designing it for lowest cost. Sorry. Okay. With regards to emitters, our lab has taken commercially available online emitters, as you see here, and redesigned the internal geometry of the emitter to operate at about 70% lower water pressures than the original commercial emitters that we started with. We got these manufactured with the help of our partner, an irrigation company in India, and we've been testing them for the past 2 years in dry regions in Morocco and in Jordan. So in this plot, you see data from a full irrigation season in 2017 using our lab's design low-pressure emitters compared to other conventional emitters that we bought locally in the market. And in the top half of the chart, you see the emission uniformity, basically how uniformly is water being distributed throughout the entire field, and the field size was about a quarter to a half hectare. And in Jordan, our uniformity is very similar. In Morocco, so all the data in green is for low-pressure emitters. The data in orange is for the commercial emitters we bought locally. So you can see that in Morocco, the uniformity of the low-pressure emitters is slightly lower. However, in all cases, we are above the industry. We are above 80%, which in industry is considered good. And on the bottom of this chart, you see the hydraulic energy that was used to deliver water to the crops throughout the irrigation season. And the hydraulic energy is just the flow rate times the power. The flow rate times the pressure of the water in the pipes. And you can see that overall there's about a 50% energy savings to deliver the same amount of water using our redesigned low-pressure emitters. And because these emitters are manufactured identically to the commercial emitters using the same materials, there is no increase in cost associated with them. So we hope that by using them, we can reduce the cost of the entire system, because at lower water pressures, you can use a smaller pump and a smaller solar array. So we are now focusing on the second approach, which is looking at the system as a whole and redesigning it for lower pressure. And to do this, we are developing an integrated system model that consists of several submodules that make up a PV drip system. First, there's the agronomy, where we calculate the crop water requirement throughout an irrigation season that depends on the local weather. Second, we have the hydraulics, where we calculate the pressure drops throughout the piping network. And we have the pump and power system, where we calculate the size of the solar array or battery required for our pump. In our model, we also can simulate energy storage in an elevated water tank or in batteries. And it's important to note that a lot of these submodules are interconnected. So for example, the weather and the solar radiance influences the crop water requirement, but also affects how much power we can produce from a solar array. Similarly, the water requirement of the crops determines, and the hydraulic system determines the runtime and the power required for the pump. So it's this interdependence that drove us to create our own simulation tool. There's already software that can simulate the different submodules. For example, FAO's CropWatt tool allows you to calculate crop water requirements. There are several pieces of software to simulate hydraulic networks. And there is solar pump sizing software that's distributed by the pump manufacturers. However, there isn't an easy way to transfer information between these tools because some of them are proprietary, and this information transfer has to happen very quickly if we are running an optimization algorithm. So we believe that comprehensive system-level optimization is not possible without a tool that simulates the entire system. And again, our overarching goal is just to reduce the costs of these water-saving irrigation systems to help smallholder farmers produce more crops and increase their income. Now that I've introduced the model, I will pass it on to Fiona, who will talk about details and our ongoing validation efforts.
Thanks. So let's see. There we go. So as Julia mentioned, we want to create this integrated model so we can look at all the subsystems. And this just shows the architecture of the model that we've been working on. So you have the different subsystems represented as modules, which are shown in blue. So we've got the agronomy, the hydraulics, the pumping, solar power module, and then the crop yield. And then we have a set of inputs that come from databases and our user-based inputs. So the goal here is to be able to ideally model a system for any location and any crop type. So we have inputs into the agronomy module, which are the local weather data and the crop properties of whatever you're trying to grow. And then the inputs to the remaining modules, which are the specifications of all the equipment that you saw in the diagram in the previous slide. So if we take a closer look at how this all works, the first two modules essentially do a simulation. So you give a location in your crop type, and it sets up a field and tells you how that's going to operate hydraulically and what the demand is going to be. And then the next two modules are more of the design of the drip system. So we look at selecting equipment, the pump, and the power system, which can include PV, battery, and tank as energy storage options. And then finally, we want to assess the performance of this proposed system. So we look at how reliable will the system be to deliver the water that this particular crop needs throughout the season, and then we look at how that relates to yield and how that will relate to profits that the user will see. So the iteration between the design and performance assessment sections is essentially our optimization with the objective of maximizing the revenue that the farmer has. So looking at the profits they will gain from the crop yields minus the life cycle costs of the system design that you propose in your design section. And all of this is subject to a set of constraints, which are that the daily water requirement is met for the crops with a certain reliability that you put in, so it could be 100%, 90% reliability, that you can't use more power than the available irradiance for obvious reasons, and that the hydraulic network behaves as you have simulated it in your design. So if we look even closer at what's happening in the design phase, Our algorithm looks at two things. First, it looks at sizing the equipment, so how big are your PV panel and battery and tank going to be? And then it also looks at the energy and water flow through the system, so it decides at every time step what that's going to look like, and in so doing can select an optimal operation scheme as well as design for the system. So, oops, one more. So when you get down to assess the performance, your operation is reflected in the objective because it determines how much water gets delivered to the crops and therefore how much profit you see from the yields. Okay. So when we first started developing this model, we wanted to look at if it actually works. So in our first design phase, we had a more simplified version that we then went on to validate. So in this simplified version of the model, the design portion is only looking at the sizing of the power system, and we're looking at minimizing the capital cost of that system because we know from previous research that the power system is one of the most costly pieces. And so we're not looking at the crop yield quite yet, just looking at minimizing that capital cost while still meeting the reliability for the system. And this is subject to the same constraints as the more involved model, except that here we're prescribing the operation scheme, so we're assuming that it's going to operate a certain way all the time. All right, so to benchmark this just on a software level, we wanted to look at how our proposed design compared to that proposed by an existing software. So a company called Lorentz has a solar pumping sizing software called Compass, which essentially sizes PV pumping systems for any application. And from the beginning, we can see that our model offers a little bit more flexibility than this software tool because the Compass tool does not have any energy storage options, so it only looks at direct drive PV options. They use an average daily water requirement as well as an average monthly solar irradiation, whereas we are calculating these values based on local weather data that we input into our model. And then, of course, because it's a commercial software, the only pumps available in their system are their own pumps, whereas we're not prescribing a certain pump type. And so just from running these two models next to each other, we found that our model suggests a direct drive PV system that has a 37% lower capital cost than the Compass design. And the way that we achieve this is essentially by downsizing the panels that we have. So that's great and encouraging, but we wanted to know if we built that system, would it actually work, or would there be any issues from downsizing the panels? So we went back to two of our sites in Jordan and Morocco, which had emitters laid out from previous trials, and we retrofitted them for solar operation in the 2018 season. And so if we take a look at a snapshot of the data from that, what we find in terms of the power consumption of the system, this shows the solar power available from the panels, so basically the power that the pump could use, and then the power consumption of the pump over a shorter time frame so you can see the details, but we took this data over the entire season. And what we see is that we're not power limited by our downsized system, which is good. However, you might notice that there's still a lot of available energy here. And part of the reason for that is when we run our simulation, we're using an average weather, local weather, that we assume is the way the weather's going to behave. That's not obviously the case. So in future iterations, we're looking at having more robust weather data input. We also, our partners in the field decided the irrigation schedule, and so we were predicting that there would be slightly longer irrigation times, and so you can see here it's only about 2 to 3 hours. We were thinking more on the order of 4 to 6. And then finally, the trial fields, the research fields we were using are smaller sizes. So if we were to expand this, say, to a larger field or have farmers irrigate multiple fields in succession, they could take more advantage of the rest of this available power throughout the day. So if we want to then see how our system performed in terms of delivering the water, this is the predicted requirement of crop requirement of water over the entire season. And in blue, we have the water that our system delivered. So you can see that for the majority of the time, our system is delivering at or above the requirement that we predicted. But there are some times when when we're not delivering the water here that we need to. And again, as I mentioned on the power side, our partners were controlling the schedule, so there were some days when if it rained or they had delivered a lot of water the previous day, they would have shut the system off. And again, our prediction is based on average weather data that we're assuming that's how the weather's behaving at that time, which may not have been the case. So in order to improve this in the future, okay. So moving forward, what we want to do is to do a similar validation where we look at how well our optimal operation scheme would work. So as I mentioned, we were prescribing the operation scheme, so we want to optimize it and then test that in the field by using a pump controller that we're developing in our lab at the moment. We also want to look at optimizing the pipe network layout. So that's assumed to be an input. We say, here's the field, here's how the pipes are laid out. But if we actually optimize the design of that layout, we can lower the pressure even further and reduce the size of the power system even further. And then finally, we want to improve our crop yield model because this impacts the profits that we're predicting. So having a better understanding of how the water we're delivering is going to actually affect the crop yield will help us design better systems. Okay. Yeah. So in the long term, the goal of this optimization tool is to be a flexible design tool for the development of these systems for smallholder farmers globally. We want to make sure that this model is robust in terms of the weather inputs, especially in terms of climate change, because we know that will alter how we design our systems. And we also want to look at alternate settings. So the ones I showed you were for surface water, but we want to also look at groundwater sources and gravity-fed systems because those are prominent for smallholder farmers globally. And ultimately, the finished tool could be something that engineers or NGOs or government organizations could use to design affordable PV drip systems for smallholder farmers in their region. And thank you.
Now, for the question and comment?
Yeah.
I have a question. I got one hobby that you should go for. It's just a simple question.
Yeah.
It showed us available solar power versus power to pump. Those available solar power you measure, yeah? So it's electricity. But it's not per square meter or any unit of solar panel.
So that's the power our system has available. So we've already multiplied it by the area of the PV panel that we installed. So that's based on that specific design.
So, and this is more than 1 square meter. So it was about 500
It
volts.
was 2 panels, right?
So it was 2 panels.
It was two
Yeah, it
panels.
was 2 panels.
And you have specific catalytic power. So you can say, for example, cubic meter of 10 cubic meter of water, how much power you need to get from. So can you say?
Yeah. We also know the pump efficiency, so yeah. That's how those two things are combined.
To the,
Do you need to change those pipelines every year?
No,
The pipes?
so that the question was, do they need to change the pipes every year? That depends on the quality of the tubing that they're using. So there are, if you buy some very, very cheap tubing, it's only meant to last 1 year, perhaps. But there is thicker tubing that's made with thicker walls, and that lasts for usually 10 years or even more. So in the US, for example, drip is used sometimes, but the farms in the US are usually of a size, like they're just huge. It's not feasible to use drip irrigation. But in the places where it is used, they use subsurface drip. So they bury the lines under the soil, and that allows them to move machinery and all the stuff above the tubing. And when they bury them under the soil, those are rated for about 20-year lifetime.
I thought this was great, and I think this has like a wonderful amount of potential. To extend the idea further, have you thought about So put you on the spot here. Could you incorporate like real-time optimization into this? Like, how could you incorporate data from drones, satellites?
Yeah, so that's something we're actually looking at, potentially working with some companies that are doing that. And so the most extreme version of that is putting sensors all over the field, measuring the weather, and making decisions on the spot to, operate your system. We haven't looked exactly into the pricing of that, but it could get expensive. So a intermediate step would be to essentially run this model through different sets of weather data, average weather data, dry year, like wet year, a bunch of different ranges, and essentially define a robustness metric for your system. So your system might be oversized for some years, but it would be properly sized for others. So that's a low-cost way of doing a more real-time design. Yeah.
Yeah. But we do need to somehow decouple design from operation because we just run a design once, right? But then operation might change day to day. So kind of thinking about those two things separately is an interesting problem.